Yeah, okay. Hello, everyone. I hope you had a great day so far. Uh, Before we start talking about the concepts of today's session, I wanted to announce that since I didn't yet receive the hardware component that I ordered for you for your assignment, uh, to be honest, at this point, it's not possible for you to reach the due time, the hardware assignment, due time of assignment one. So I'm gonna extend the assignment one uh, until the February 23. So now assignment one and two have the same due time. Okay. Hopefully we get those parts soon and you could get started on your assignment and but the simulation wise, you don't have any problem. Okay. The due time is extended, but you are now able to run the simulation. You already have enough information. I will upload some kind of hint video or tutorial videos during this week and next week in order to help you have an easier kind of process to do the simulation on MATLAB. Uh, but regardless of that, I really encourage you to start if you didn't start it yet. Okay. Now, before we start week three concepts, is there any question about our previous week, the discussion that we had about the PWM and the switching strategies that we uh, takes in order to control or uh, use our inverters, okay, signal our switches and activate, in other words, our inverters in the system. Any question about the PWM, the concept of the switching, the concept that we discussed in week one about topology? Any question? No? Okay, let's start the next uh, concept. So far, we talked about the inverters. We gone over the topology of the inverters. We talked about the half bridge. We learned how they work, how we could model them, how we could develop the equivalent circuit for those inverter topology. We learned what are the more advanced inverter topologies beside half bridge. We were introduced to the full bridge, to the multi-level inverters, the three types. We said which one is the best one. We compared, as a comparison, we talk about the three multi-level inverters and we talk about that. Then after the topology, we get to the control strategy that we take in order to use that inverter topology, or in other words, the technique that we use to create the switching strategy. So we could signal our topology, control our topology in order to have our desired waveform. We learned about the pulse width modulation or PWM, and we said, okay, this is the main kind of concept or main strategy when we talk about the inverters and control of the switching of the inverters. Okay. We learn about the sinusoidal PWM when we had a reference signal, which was a pure sinusoidal or desired waveform in a power system. Okay. And we learned, okay, how that works, how the carrier and reference signal work together to create the activation or deactivation signals for the gates of the switches that we have, or MOSFET or IGBT, whatever is used in the topology. But during that, we learned that all those pulse width modulation, which is in the name, they work in a way that cutting off a DC voltage, basically creating an arrow of square waves, which we call it pulse, in order to mimic our desired waveform. You remember that? We already talked about that. But we know that, however accurate we could do the switching, we never can reach the point that by switching, we could get a pure sinusoidal voltage. But at the end of the day, we always going on and off on a DC voltage. So we are creating a bunch of square waves, adding them together, okay, either in parallel or in series, okay, and then try to get close to our desired voltage. That means we always have a distortion. Okay, today we are going to learn about how we could quantify that distortion. Okay, and since it's in the name, it's a distortion, it's not desired for us. So how we could get rid of it, or at least make it less effective, less harmful for our system. Is that clear? Like, makes sense that past that we gone so far, and we're going to continue. Topology, how to ignite our switches. Now the problem of that control strategy that we had, which is the distortion that we have compared to our perfect desired waveform, which is a sinusoidal. Are we good? Now, we learned that, actually you learned that probably before this course, but we already talked about that. We could take advantage of certain mathematical tools named Fourier transform or Fourier series, okay, and describe any arbitrary voltage as summation of a bunch of sinusoidals with different frequency. Okay, and when I say bunch of sinusoidal, I mean from 0 to plus infinity. So that bunch is quite wide. Okay, so the range. Taking advantage of that technique, we try to describe our pulses that we make with PWM or SPWM or SVM, all those techniques that we get introduced to. We try to represent each of those pulses, okay, as a summation of bunch of sinusoidal with different frequencies. Now, at total, in our PWM, we have a series of those pulses. Superposition. So it's going to be the superposition of all those bunch baskets of frequencies. Make sense? So for example, as you could see in the picture, the image try to illustrate how we could mimic a pulse in a square wave, okay, using the summation of different frequency. Okay, now I assume you already know about the Fourier series. The Fourier series, based on the definition, would contain all the frequencies from 0 to infinity, meaning it has a DC part plus the term that we like. Okay, so we gonna take it out of the summation. Okay, the fundamental frequency, the desired waveform that we like. For example, in power is the sinusoidal with 60 hertz or 50 hertz outside of the United States. Okay, so and the rest of the frequency we put them as distortion. We don't want them. Okay, we can get rid of them because you're switching, but you don't want them to respond. Okay, now. Okay, as we said, the desired part of the Fourier series equivalent of the arrays of the pulse that we make is our desired voltage. So we are focusing on that. Our purpose on any technique that we make is to keep that on the level that we want. For example, if you wanted to like have 110 volt at your terminal, like the plug-in, okay, for example, you wanted to like go tailgating, like, or like, you know, going to a trip, you wanted to like power your TV from your car batteries, okay? So, or your car generator, which is a DC generator, okay? You want to have an inverter that creates the level of voltage that TV wants, like 110 volt, a stable and precise. So what we want for our fundamental component is to be at the level as we want and stable. Now, yeah.
Actually have to invert to a 12 volt, like regular electrical outlet. What is the,
What do you mean?
like when you use a cigarette lighter,
Okay,
voltage or power, is that DC? And
it is this.
And
The output of the car, either the generator, that I think we call it DINA, right? I'm not sure. What you call the generator of the car in the United States? The one that charges the battery?
The
alternator.
Alternator. So you have the alternator, both alternator and the battery is the output is DC in the car.
Okay, and so
Okay.
is it, so it's not 12 volt, then if it needs an inverter, is it like whatever the?
The level of the voltage is different based on the car. Okay, it could be 12, could be 24 in the trucks. Trucks work in 24 volt. Okay, so it could be different, but what you want out of it
But it's going
based
to
on
DC.
your application, yeah, it should go to the AC. Okay, yeah. So we have a fundamental frequency. Based on the Fourier series, we have a bunch of other frequency. Ideally, they should be integer multiple, okay, of our fundamental frequency. But we know in practice, not going to happen. We already talked about that. We are going to have some non-integer values, okay, of multiple of our fundamental frequency too. But ideally, it's defined as fundamental omega 0 and n times omega 0. Now n changes from 2 to infinity. Okay, and we have our other sinusoidals, which we call it harmonic. Now, the harmonic distortion is all of those harmonics all together. Okay, so it's not just one harmonic or one specific frequency, all of them all together. Whatever we have beside the fundamental frequency is distortion. Good? No. One good thing about the pulse or like a square waves, when you look at the square waves Fourier series, they have a little bit of a very good kind of like characteristics. One characteristic would be all the harmonics that exist in a Fourier series of a square waves, they are all odd numbers multiplication of the frequency. So if our fundamental frequency is 60 hertz, in PWM, we don't see, because of the symmetry of the shapes, we don't see 120 hertz, which is twice the fundamental. We only see the 3 times fundamental, 5 times fundamental, 7 times fundamental, all the odd multiplication of our fundamental frequency. This is because of the symmetry. You have to like search about it, Google it, how it would work, why we have only odd multiplication of our fundamental when we have a square wave. But the short answer is the symmetry of the wave, but search on that. Let's dig into that to get familiar with the reason and what the behavior of the Fourier series is based on the waveform of our actual voltage. Now, beside that advantage, which basically help us a lot on controlling distortion, because automatically it get rid of half of the harmonics, all the even numbers are gone. Now, the coefficient, if you run a Fourier series on a PWM, you will find out that the coefficient of each of those frequency is gonna be 4 over n pi, okay, times the VDC, which we have. So here at this equation, I consider a per unit. So VDC is 1 volt. If it's 1 volt, each component, the amplitude of each component are gonna be 4 over n pi, okay, times that 1 volt DC. Now, as DC is 10, it's basically 10 times that value. So what is n? N is the number of harmonic. So fundamental harmonic is the first one. So it's 4 over pi times whatever VDC you have. This is your amplitude of fundamental frequency. Now, we don't have second harmonic because of the first characteristics. The third one would be 4 over 3 pi of these, the amplitude. 4 over 5 pi. So you could see when we go up when we're rising the frequency, the amplitude goes down. Correct? So from a certain point, practical wise, from a certain point, it doesn't make sense to even worry about those harmonics because they are so low that we can get just neglected. Are we good? There is a standard for that, for the harmonic control, for harmonic distortion in a power system. There is a standard for that. I think I mentioned that somewhere in the slides. I will take a look at that. We would see that. But that standard describes how much harmonic you could have and how far you have to go from the frequency. Okay, so you draw a threshold of what frequency you could neglect, those high frequencies, in order to calculate the distortion. Because the frequency goes to infinity. If it goes to infinity, that means we cannot calculate the distortion. Okay, make sense? Are we good so far? So because of the special waveform that we have, we have to the very good kind of like characteristics of our Fourier series that make our life much easier when we want to like analyze our harmonic distortions. Any question about that? No? Now, why even bother to do the Fourier series or harmonic distortion? First one, we already know because it's a waveform analysis. We want a desired waveform. Any harmonic is the deviation from that desired ideal point. So we want to know what's going on. Okay, what's going on in our system. The second one is that if we don't know what kind of harmonic or what frequency of the harmonics we have, we cannot control them or mitigate them. So we have to target them. It's not like we could deal with all of them at once. Okay? Why we should do that? Because as much as deviation that we have from our desired sinusoidal perfect waveform means that we are off on power quality. Let me give you an example. Let's say you have an AC motor, okay, that the induction motor that works with the output of an inverter. Okay. The induction motor, the speed of the induction motor, okay, or synchronous machines, either way, the speed of the rotation is equal to the frequency of the voltage that you supply to that motor. Are we good? So induction machines rotate with the same frequency that your voltage has. So if it's 60 hertz, it would have the same frequency, same speed. Okay? Now, imagine if you give two waveform at the same time to them, one is 60 hertz, another is 180. Third time of 60 hertz. The third time. What's going to happen to the speed of that motor?
It's gonna go faster.
It's not going to go faster precisely, okay? Because as we talked about that, when we talk about the AC circuit analysis, one frequency at a time. We cannot combine two frequencies in one analysis. Okay, so what we have to do, if we want to like see what's going to happen to that motor, we have to once do the analysis based on 60 hertz, find the result, which is the normal kind of like operation, then go back, cancel out the 60 hertz, add a 180, and see what's going to happen. One frequency at a time. Okay, now we have two results for two analyses, one for 60 hertz, one for 180. Superposition give us the opportunity to have the overall effect of the two by adding the two results of the two different analyses together. Now, you have a 60 hertz, the machine that works with 60 hertz, and the machine that works with 180. But the power of 180 is lower because it's harmonic. Okay, so in reality, what you see is a bunch of like rips on the rotation of your motor. Because 60 hertz wanted to like have a smooth rotation, but that 180 would kick in once in a while, and you have a distorted rotation. It's always ripples. Now imagine we have the fifth harmonic, another ripple, the seventh harmonic. You know what I'm saying? So it would disturb the quality of the power you get and you use. Make sense? This is from voltage part. Now,
They would have to be perfectly in phase and the same amplitude in order for it to increase in speed steadily instead of doing the.
they will not, because they are two different frequency.
I know, but that's what I'm saying. I'm saying in order to do so, it would have to line up every single time. It wouldn't be.
If you have two frequency, you would never have a smooth rotation. Doesn't matter what is the frequency, because what is the amplitude, okay?
No. Even if it were, I mean, I'm saying like, if you didn't have the extra, it would still have to like line up, and most likely if you have another source, it's not gonna line up as well.
Yes. Here. So what's gonna happen, like this is like one example of voltage frequency. Now, what if we wanted to like describe the harmonics from the current perspective? Okay. Anyone can tell me what's gonna happen in a system, in an AC system, if we have higher harmonics of current in our system? Anyone can guess what would be the immediate result of having a higher harmonic current harmonics? What is the main rule in AC circuit analysis? The first main rule in AC circuit analysis. What law we have, which is the baseline of the AC circuit analysis, or even like circuit analysis, it doesn't matter. The first law you learn in circuit one. Ohm law. Okay? Ohm law says the voltage is equal to ZI in AC. What is Z? Impedance. Impedance changes with frequency. Correct? Because the real part was resistance. We say it doesn't change with frequency. Okay? But the imaginary part is the inductance, either J omega L or minus J over omega C. So if I have a higher, and power system normally is a RL system. Okay, L is much higher than C. So you mostly see such an impedance. If I wanted to like have a harmonics in my system, what that means? That means those harmonics, those high frequency harmonics, see higher impedance. Makes sense? Because omega is higher. So in 60 hertz, we have Z1, but in 180, because the frequencies change, we have another Z when we describe the system. Remember the rule. When you want to analyze a system, one frequency at a time. You cannot mix frequencies on AC circuit rules. Okay? Now, if we have higher impedance, what that means power-wise?
A lagging.
Lagging, more general. You have higher impedance. What will happen to your power? Your power goes down. Why you go down? Dissipates. You have a more loss. So more harmonics means more loss. Are we good? What is more loss meaning? Higher temperature. Our problem. Do you remember that? Our main problems. So these are the reason that we don't like harmonics and we have to get rid of them. These are why they are considered as power quality issue. Because they introduce other frequency into a system, mess up our applications, and add more losses.
Not to mention nature.
Yeah. So how we could quantify that harmonics? As I said, we have several frequencies that create that distortion. All together create that distortion. We are going to introduce, in order to quantify the whole distortion, we are going to introduce a factor named THD, total harmonic distortion. THD is the main factor in order to analyze harmonic distortion in power system. So you are going to work with THD a lot. Okay, but it's very easy kind of like concept. Is the overall effect of all the harmonics compared to the fundamental. So what we do is we calculate the root mean square of all the harmonics amplitude from 2 to infinity. Okay, all the V is squared, added together, and then square root over the fundamental. Is that clear? Now you have THD normally is represented as a percentage. Okay, so now you have THD. Same goes for the current. For the current is the same. Like instead of the voltage harmonics, you have current harmonics and fundamental current. Make sense? Is that clear? So this is how we could define or calculate, okay, harmonic distortion in our system. The image kind of try to like represent what is the difference of the harmonic distortion. Like you see, sinusoidal only have fundamental frequency. Okay, if you do the Fourier series, this is the FFT or Fourier series of our voltage. If it's sinusoidal, we only have one frequency. Out of inverter, our square waves have all different frequency, and you could see that amplitude is decreasing when frequency increase. Okay, and all these frequency all together shapes this THD. Make sense? Are we good? No. No. I want to ask you a question. Why we did not just calculate a root mean square of all the harmonics? Why we have to like have the fundamental in denominator? Anyone can guess? Because fundamental is not a harmonic. But when we wanted to like calculate the THD, the total harmonic distortion, we include the fundamental, okay, in the formula. Why we have to do that? Ratio for what? Like, let's say you,
Instead, like, base level, like if we did divide it, then we would, our base level would be off.
yes, that makes sense. Let me add on to it, okay? Later on, you would see that by manipulating like the frequency, the switching frequency that we had in PWM, or the pulse width, or the reference signal, okay, by controlling, manipulating that, we could change the level of the harmonics because we are changing the pulses. Okay, now, if we haphazardly change those pulses in order to just minimize the harmonics, what would be the cost? Are fundamental. Because yes, those factors affect harmonics, but they also affect fundamental too. So in order to save ourselves on a cost of deviating from fundamental, we incorporate fundamental into our harmonic distortion quantity. So we make sure that we do not limit or mitigate harmonics in a cost of losing our fundamental.
That's just like impedance matching, except it's.
Yeah, tying the same concept. Yes. Is that clear? Any question about that? When we have harmonics, okay, we use PWM in order to ignite our switches. Okay, now we could manipulate the parameters in PWM in order to change the level of harmonics because we are changing the waveform. Is that clear? Okay, now if we wanted to only limit or mitigate the higher frequency, okay, if it's the only goal that we have, we could manipulate the switchings in order to reach that goal. But that means we are manipulating the overall waveform, which also creates the fundamental, not only the harmonics, but also the fundamental. Okay, so what we did basically was to get rid of the harmonics with the cost of not having our desired fundamental. Now, in order to make sure that our fundamental is safe, now we are reducing the harmonics. We incorporate the fundamental into our quantification of the harmonic distortion, so we could keep track of what change we made. So this basically the harmonic distortion become a relative value to the fundamental. Okay, so we just not directly go to hit the harmonics. We want to hit them relative to fundamental. Did I answer the question? Is that any question? Is there any question for in that concept?
So you said basically you add the fundamental together so that it changes the harmonics relative to the fundamental value. But how does that is it because it's taken into account like the fundamental of each harmonic?
Okay, let me give you a very, very kind of like simple example of reducing the harmonics. Okay. If I want to purely reduce the amount of harmonics, but the nominator of that PhD, only nominator. The very, very, very basic thing that I could do in the PWM is to reduce, that was our PWM, remember? and this is a signal, reference signal. If I reduce the modulation index, so damp my reference signal, what's going to happen? All the amplitudes, all the harmonics are going to be damped. Is that right? So if I will push this reference signal towards zero, my third frequency, my fifth frequency, my seventh frequency will significantly decrease because the amplitude is decreased, correct? But I also decrease my fundamental significantly. If I only have this value, suppressing the kind of like decreasing the modulation index, meaning the better THD, because I only have the harmonics values affecting my uh, uh, quantity of distortion. Now that I have the fundamental in the denominator, okay, because this decrease in the modulation index caused the decrease in a fundamental, that would cancel out the effect of such a technique in order to decrease the THD. Make sense? So it would prevent you to kind of like trick yourself that I'm gonna get rid of the harmonics, but in fact, you are disturbing the whole system. Did you get what I'm saying? Is that clear? This is one example of what's gonna happen. Why we incorporate V1. So we wanted to like control the harmonics relative to the fundamental. This way, the fundamental is our reference. Now we wanted to like reduce the level of harmonic in a percentile of the fundamental. Make sense? Are we good? Now, how? Okay, we already talked about that. Now, how we could mitigate the harmonic? One thing to say to tell you first is that we are not going to be able to eliminate all the harmonics. So reaching a THD equal to zero is impossible. Okay. Now, I put a general equation of the Fourier series for the PWM signal. Let's say that voltage V of t is the PWM signal that you have at the end of your half bridge or full bridge or whatever you want. Okay, so it's a general one. Okay. Each harmonic has an amplitude that's C, and M. Okay. E to the power of j is that cosine and sine. This is the Fourier series. Okay, the summation of all those sine and cosine. And you could see that the harmonics or the frequencies or the phases of all those different frequencies are going to be described or are going to be shaped based on the fundamental frequency that we have, which is basically the reference frequency, the frequency of our reference signal, okay, and its multiples. The carrier frequency that we have, because we saw before, we talked about that frequency of the carrier is also parameters in output, okay, and its multiples. Are we good? The initial phase angle that we have for our reference frequency and its multiples, the initial phase angle that we have for our carrier frequency, carrier waveform, and its multiples. Is that clear? So we have several parameters in our PWM system, in our PWM techniques, that affects the component of our Fourier series. The two frequency, the two initial phase angle, and we already know that we have modulation index shaping the amplitude of our main component. Are we good? Is that clear? Knowing that, we try to find the solution to eliminate or like decrease those harmonics. One solution would be try to manipulate the switching technique that we had. We already know from the formula that we have FR, FS, phi R, and phi S plus MA that we have, okay? So far we have 5 degree of freedom in order to manipulate our PWM technique. If we change those factors, it would change the output of PWM. Make sense?
Since you said that M was the modulation, would it not be multiplied by?
This M is not a modulation.
Oh.
Not yet. This is the multiple integer of fundamental frequency. Is the yeah.
Minus 5.
So we already have 5 factors that you could see affect the Fourier series that we could control in our SPWM strategy. So basically, you could run a code in MATLAB, an optimization code, to find out what kind of configuration of these 5 kind of like parameters will give you the best output, the best possible option of output. Make sense? So we have the 5 degree of freedom on optimizing our output, only focusing on PWM harmonic reduction. So this is the first level of reducing harmonics. So we optimize our switching. We don't haphazardly switch. Are we good? Is that clear? Next level is some advanced control. We are going to see what kind of advanced control we are talking about, okay? Which creates not only we have control over those parameters in SPWM, but also we create a dynamic control in advanced system. A dynamic control. So it would react to the change too. For example, if you have a machine learning technique that controls those two, then you would have a real-time response to whatever happens in a terminal, and you could optimize in real time. Does that make sense? You have a question?
Yes. When you say optimize with the switching as the first level, in a real world case, would that be an example of the PLC that gets set up?
PLC that gets set up somehow, not precisely. They don't use programmable kind of like act that. Currently, in the current version of inverters, they don't have an active optimization technique inside the control system. So they normally have a pattern recognition. So they use fuzzy logic. Anyone is familiar with the fuzzy logic?
Yes.
Fuzzy logic is pattern recognition. So
It's
yeah.
what ML.
It's a kind of like an older version of the machine learning. Okay, you train your data, you have some patterns, like they say, okay, if this happens, I have to act like this. Now you have, if I observe this, I would act like this. If I see something going toward my head, I'm gonna duck. So this is something like that. So, okay, and now you try to have a table of all the possible problems that you could have, and the optimized answer to those problems, and save them in your control system. So if it sees something close to one of those options, goes toward that answer. Like pattern recognition system is a fossilized. Okay?
Like putting intuition into.
Yeah. Normally the current version of the inverters, okay, try to do that. Okay. It's very like the real-time advanced kind of like control of the inverters is still in a research phase. Okay, it's still in a research phase. Now, as we said, no matter what we are gonna do or control or like switching signals, we are still creating a bunch of square waves, a bunch of poles. That means doesn't matter what we do, we are still gonna have some harmonics at the end. We could reduce them, but not get rid of them. How we could add another level of protection, another level of correction, then the filters kicks in. You do your best on switching, but at the end of the circuit, you put a low pass filter for like power system or band or whatever kind of like filter that you want to like the design. Normal design is low pass filter. Okay, you put a low pass filter to damp all the high frequency harmonics and let go of the low frequency. So basically, you try to either like with the techniques, the harmonic techniques, you could target a specific frequency to eliminate, and then you have a less harmonic. Then you put these less harmonics into the filter and you damp them to the level that now it's okay, I can tolerate that level of harmonics. Make sense? This is, yeah.
At what point does, like changing your configuration, like the delta configuration? It's supposed to.
What do you mean by delta?
The delta for, like when you're looking at star or Y versus
Oh,
delta.
that's something different. That's something different. It goes to the when after the midterm when we talk about the system perspective of the inverter based resources, then we talk about the because
So much later.
yeah, delta and a star is characteristic of our system, not our component. Any questions so far? No? Okay. So based on that, we already know, okay, we have SPWM techniques, okay? The first option was to create or optimize switching technique, SPWM. We already know what is the SPWM is. We already talked about that. And we wanted to like just use the degree of freedom that we have on the SPWM in order to decrease the harmonics. Now, if you remember from the formula, and I don't want you to like forget that, you could see that those components, those harmonic components, okay, one way is to get rid of the harmonics because we are going to have a low pass filter at the end of our circuit, okay? It's basically logic, okay? If we have a low pass filter, one way to eliminate the harmonics is to push all the harmonics to the much higher frequency. Okay, it's basically like we pushing them to a so the filter will just lower them, something like that. So we push them toward the high frequency in order. So okay, we all know that okay, there is a filter out there that would get it off. This is one strategy. Okay. Now you could see the frequency part of each of our harmonics is n times reference frequency, that's 60 hertz, plus the m times switching frequency. Meaning, if I increase my switching frequency, I basically push my harmonics toward higher frequencies. Make sense? Is that clear for everyone? So now filter has a easier time to get rid of them. So this is one way to get rid of those harmonics. But there is a trade-off. If I increase my switching frequency, we already talked about that when we talked about we introduced the MOSFET and IGBT in the first week. What would be the consequence of that increase in the frequency? power loss because the switches has loss when they go on and off. You would have some power loss. Because of that power loss, we said that there is a very high temperature rise in switching devices. So if I increase my frequency, I have to deal with that power loss and high temperature too. So there's a trade-off. So I'm gonna make sure that I'm not go too high in order to like damage my circuit. But I can manipulate that frequency in order to push the harmonics forward. Make sense? Okay, this is the same concept.
So is there any way to use a mixer and do modulation like in digital signals with the system?
You mean like having it uh
To do what-
no yeah. Yeah, actually like there are. But the cheap inverters doesn't have that. But the industrial version of the inverters, uh I try to like show you one of the circuits of industrial inverters. We have that in our lab. Uh, those normally use digital kind of like electronics. Okay, so they have microprocessor that do the all the optimization. Okay, based on the signal. So like Texas Instrument has a chip for getting real-time FFT. Okay, so there's a chip that observe the terminal, calculate the Fourier transform, give it to the microprocessor. Microprocessor can optimize the switching to reduce the harmonics that exist and ignite the switches based on the new PWM. This is like what it's happening in industrial scale inverters, but it's too expensive. So in like cheap, like household kind of like scale of inverters, they don't do that. They just use a simple analog oscillator for the PWM. Did I answer your question? Okay. Now we said, okay, frequency is one of our uh, degree of freedom to manage switching frequency. Why I'm insisting in switching frequency as one of the leverage that we have and not reference frequency?
We can't control the reference frequency, but we can control switching.
You can't control reference. This is what we create. This is our signal. We create reference signal, we create carrier frequency. Both of them are, why?
For some reason, I thought you were asking like one signal was what was coming in from from the system that we can't control, and one was what we were doing.
This is the PWM, right? The carrier. This frequency is Fs, and we have a reference which has Fr. Okay? You could have a feedback loop to observe the terminal and create the reference signal that you want based on what you observed. Okay? What I'm asking is that why we cannot use or we should not use the reference frequency as a leverage to change the harmonics level. Anyone has any idea? What is the significance of the reference frequency? What it gives us? What's the output? If I say reference frequency would be 10 hertz, what would be the result of that at the output of our inverter?
10 hertz,
10 hertz what?
10 hertz of frequency.
10 hertz of frequency at our fundamental. The reference voltage, the reference signal, the frequency of reference signal is the frequency of our fundamental. So we don't want to mess with it because we want to keep our fundamental as is. Make sense? So that's why we don't mess with the frequency of our reference signal. Because if we do, we are gonna mess with our fundamental frequency. And we don't want that. So one leverage is to change the frequency of the switching. We said that there's a trade-off. Another factor that we said the leverage that we have is modulation index. We already said that, okay, we can change the modulation index. And the extreme example that I made earlier, you see that if we change the modulation index, definitely we change the amplitude of all the harmonics and fundamental, right? So that means modulation index is gonna be an effective way to reduce or change the harmonics. But we have to make sure the trade-off that we make is still another trade-off here. If we manipulate modulation index to manipulate the harmonics, we have to make sure that we are not going too much off on our fundamental component, because it also would change fundamental component. Is that clear? Now, I introduced three kind of like concept of modulation. One is under modulation, another is linear modulation, and then over modulation. Under modulation is quite simple. We already talked about that. We said that the modulation index ideally should be, the amplitude should be somewhere between 0 to 1. Correct? So this is our ideal case. If we have m equal to 1, that means both signal, the reference signal and carrier signal have the same amplitude. That means whatever happened is linear. They are same amplitude. There is no nonlinearity between them. They work at the same level. That's why they call it linear modulation. If the reference goes down, now we have to compare them. Now the relation between them is not linear. We compare them, and the comparison makes the switchings. You might say that, okay, we already told that the modulation index would go as higher as 1. So how come we have a value, we could have value higher than 1? The answer is that we don't want that higher value, but we are talking about a practical system. There is going to be some variation and errors. So there are going to be some errors or malfunction in our system that could result in a reference voltage going higher than 1 volt, or the per unit wise. Meaning now the modulation index is higher than 1. Now, it's easy for you to find that, okay, if the modulation is higher than 1, that means is going over those pulses, right? Which means our switching is going to be off our strategy. Like they don't follow our PWM strategy. Because now we can compare these two reference and carrier signal to create the ignition signals for our switches. Make sense? Is that clear? The overmodulation? We don't like it. We want to avoid it, but it's going to happen. Sometimes it's going to happen. How we can avoid it? To make sure that we are a little bit off the m equal to 1. So if there is an error, we're still less than 1. There's one technique, we keep some marginal distance from modulation index equal to 1. So we make sure that we never go over 1. But we have to know what's going to happen if we go over 1, because it might happen. Yeah.
Is this the same thing that you said?
No, that's why No. This is that I call this MA, modulation index. This MA in this formula is inside the C. I don't know if I have a formula of the. No, I didn't put that here. The formula, you remember that we said the coefficients for a square wave is gonna be 4 over n pi times VDC. Okay. Now there is a m times VDC here that describe the level of DC. Okay. This MA, this value is inside this C. Modulation index. It describes the amplitude of your basically DC voltage. Same goes if you remember we had a graph that we said if we have a switch 1 and it's cutting off like with duty ratio this way, okay, we could represent it and switch 4 that is a complement of that switch 1, okay, we could represent the overall with a value of 2D minus 1 as our modulation index for the whole system. Yeah. MA is the modulation index, so it's basically the averaging. Yeah. This M is just the multiple in the summation. That's why I use the MA instead of M for modulation index in this part. So separately. Did I answer your question? Any other question? No? Now, we already talked about that. We could manipulate the factors that are in this WM or SPWM in order to reduce the harmonics. Okay. Another way to reduce the harmonics we already know is those multi-level inspiration, the multi-level inverter that we say, okay, is easily could be seen that a multi-level inverter would reduce the harmonics. And we know why, because we have multiple carrier that are trying to switch in multiple stage in our voltage, so it would mimic a better sinusoidal at the output. Is that clear? Do you remember the image that I show you for the multi-level inverters that we had? Like we had a sinusoidal. In multi-level inverters, we have multiple carrier a stack on top of each other. Each carrier would ignite each level. Now at the output, we have several kind of like level of PWM on top of each other. Is that clear? Any question about that?
How is that?
Let me give you the I don't know if I have the no, I don't have the picture. Consider this, like you want to have a sinusoidal voltage, the perfect sinusoidal voltage. The single carrier PWM, what it does is to create a duty ratio that mimics a sinusoidal. Correct? Now, if you have multiple of those duty ratio, multiple of these signals, stacking on top of each other. Like I have this, now I have another one. And another one. Okay? When I add them, put them in series, they are gonna add to each other. So what's gonna happen? Your waveform is gonna be like this. You have a stack of PWM that mimics a better sinusoidal than what you had at first place. This is the visual kind of like answer. Now, the mathematical answer. You have 3 PW. Each of them has this formula, correct? Each of those PWM has this formula. You are stacking on top of each other, so in series. So they are adding together. Makes sense? But one has like C1, another has C2 amplitude, another one has C3 amplitude. Okay? Even considering that all of them has the same switching frequency. But the FR and FS for each of them are going to be different because in a different level. Make sense? Can you see how the initial phase would be different for the different level of carriers? This carrier sees sinusoidal with different initial phase angle than this second carrier because it sees different waveform. Is that clear for you to get? So we have 3 factors that are different between level 1, level 2, and level 3. Now they are adding together. What's happened if you have like 2 sinusoidal with different phase angle, same frequency, add together? You have one sine and you have another sine. What is the result of this addition? You could see, let's do the math. This is 0, this is negative. If you add them, it starts with negative. Correct? Don't do that. What happened? It goes higher, then this is 0, this is negative, goes higher, 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 until this, now it goes down, and now goes down more, 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 and then goes up. You see it differentiates from the original harmonics. Now imagine all the components has such an effect. So you have a wave and you have a same frequency with phase angle. I think I could have like a better view if I introduce the 90-degree phase shift. Like this is sine and this is cosine. This is 1. It goes down. When it goes down, it also goes up. So sine plus cosine. What is going to be the sine plus cosine? I'm going to show you this. This is what.
So basically, if we have a bunch of switches that we're trying to do everything to make sure that they are giving a correct signal, and we add them all up, we're going to have one final signal that's gonna have a whole bunch of data points along approximately what we're wanting. That's basically what you're saying, right? It's just like adding data points in your oscilloscope.
Yes, let me, if I sorry, I have to like, I want to find the result, please. Do you see any? Let's go to the Desmos. Sine of x plus cosine of x. This is sine of x, and this is cosine of x. What happened? No, 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 no. Cosine. Do you see the green line and the what happened? Oh, I thought you already had the. Come on. Okay. The green one and the blue one, okay, consider them as a sinusoidal or one frequency with 90-degree phase shift. I'm going extreme to show the effect. Now you could see the red one, okay, is in a different level. Now, if I manipulate this plus 1, plus 1, see how it decreased? I'm getting phase shift. I'm just introducing a phase shift. How it decreased? If I do plus 3, it increased. So by manipulating the two waves interacting with each other, okay, I could manipulate the level of that frequency. Is that make sense now? Now you have multi-carrier. Now you have multi-carrier frequency or multi-level inverter. Okay, each of them creates their own Fourier series. Now, each of them introduce 180 hertz harmonic, but they are in different phase angle. So when they are acting together, adding to each other, the overall result would be something else, either decrease or increase. Is that clear? Now, how can I control that phi R and phi S was under my control? So I can control how they are out of phase with each other. So I can make sure that they are in a phase that when they added together, they would eliminate each other or decrease each other. Did I answer your question?
Yes, we mean by controlling those.
Or decrease. So when you have multiple carrier or multi-level, you are introducing, you basically, your result is going to be the interaction of several Fourier series. Now you can manage those Fourier series in order to reduce it themselves, to cancel each other out instead of adding to each other. And have a less harmonic distortion. Did I answer your question? Is that clear now?
So the result. The result. It's also is time.
Is assignment because we have three Fourier series. See, you have a bunch of frequencies, sinusoidal with the different frequencies. You have another basket of those frequencies and another basket of those frequencies. Now, we know if you have two sinusoidal, when they added together, you know that trigonometric rules. Sine plus sine, sine plus cosine, what's going to be happen at the end? If they have same frequency or they have different frequency. They are going to interact with each other, creating new sinusoidals. Now, we want to make sure that when they interact each other to create that new sinusoidals, amplitude-wise, they would decrease. It would have that end result would have lower amplitude in compared to the input signal that we have. Is that clear for everyone? Any question about that? No? Okay. That's phase shift principle. We already talked about that. This is what we talk. Multi-carrier is part of the phase shift principle. Again, we already talked about the manipulating the carrier frequency. I passed the time, right? Sorry. Let me see how much I have. No, it's too much. Okay, I'm gonna stop here. Sorry, I lost control of the time. We are gonna stop here. At the next in our Thursday session, we are gonna continue the talking about the optimization of the switching, how we could optimize, and move fastly toward the filter design, which is basically our last defense against harmonic. Okay, so this is our gonna be our next session. Any question? No? Are we good? Okay, thank you very much. I appreciate your patience and have a great rest of the day.